In this example, we've been asked to calculate the length of the curve f of x equals the square root of x cubed on 3 from x equals 0 to x equals 2. So we recall the formula for the arc length along a function given to x values, and its s is equal to the integral from a to b, the square root of 1 plus dy dx all squared, and we integrate that with respect to x. So for that we see that we've got dy dx, that's the derivative of the function we're given. We need that in the integral. Add 1, square root, take the square root. A to b are our limits, our x values, so we know what those are. A equals 0, b is equal to 2. So before we jump into the integral, let's work out the derivative of the function. So if y is equal to the square root of x cubed, we can write as x cubed to the power of a half, or x to the power of 3 on 2. That's all divided by 3. So if that's our function y, the derivative of that, dy dx, is equal to 1/3 times the 3 on 2 comes down from the power, x to the power of 1/2. We subtract 1 off the power. The 1/3 and the 3 there can cancel, and we get x to the half on 2. When we substitute that into our formula, the square of that square root will cancel each other out, so that's good. So substituting now this derivative and our values for a and b into the formula for the arc length, we get s is equal to the integral from 0 to 2, the square root of 1 plus dy dx is x to the half on 2, all that squared. X to the half squared just gives me x. 2 squared is 4, and we're integrating all of that with respect to x. So we have a square root there which is not easy to integrate, but we notice that we have a linear term underneath. It's always a good idea to make a substitution if you have a linear term. So let's let u equal to that linear term underneath the square root 1 on x plus 4. To transform the differential, we notice that du dx is just 1/4. So in this case, du dx, or du, is equal to 1/4 dx. Or we can rearrange that to get dx is equal to 4 times du. We also see that we've got limits here. We've got values for x. When we make the substitution, we've got to change the limits as well. So let's write them out. When x is equal to 0, we just use the substitution here. X is equal to 0, 0 and 4 is 0, u will equal 1. The top limit is where x is equal to 2. Substituting that into our substitution, we see that u is equal to 1 plus 2 on 4. 2 on 4 is a half, so u will equal 1.5, which is 3 on 2. So using all that information, the integral becomes, the limits have been changed to 1 and 3 on 2. The square root we can write as a half. 1 plus x on 4 is u, so this can be written as u to the power of a half. Instead of dx, we're writing 4 times du. So I'm going to write the 4 in front of the integral, and the du is our differential. So that's turned that into a very easy integral, a standard integral. Let's work it out and then substitute in the limits to get our total arc length. This is equal to 4 times the integral of u to the half. We think of adding 1 to the power now. Half plus 1 is 1.5, which is 3 on 2. That comes out the front, but we flip it over, so it's 2/3. 2/3 of u to the power of 3 on 2, and we're going to integrate that, or evaluate that, from 1 to 3 on 2. The constants out the front give us 8/3. Substituting in, u is equal to 3 on 2. We get 3 on 2 to the power of 3 on 2 minus 1 to the power of 3 on 2. And all of that is being multiplied by this larger set of brackets here being multiplied by 8/3. So that's the end of our integral, and that gives us a value for the total arc length, but we can rearrange this a little bit or simplify this a little bit. So let's bring, I can see I've got some 3's here, I might be able to cancel 2. I can also write 8 as 2 cubed, so there's definitely some factors here that'll cancel with some factors here. 1 to the 3 on 2 is just 1. So let's multiply out the large set of brackets first, and at the same time I'm writing 8 as 2 cubed. So 2 cubed divided by 3, multiplied by this first set of brackets. A fraction raised to the power is just the top line and the bottom line raised to the power, so that's 3 to the power of 3 on 2 divided by 2 to the power of 3 on 2. The second term, 1 to the 3 on 2 is just 1. We're multiplying that by 8/3. We might as well just leave that as minus 8/3. Here we can gather like terms now. We've got common factors of 2 and 3. So the common factors for the 2, we'll get 2 to the power of 3 minus 1.5. On the top line we've got a 3, bottom line 3 and 2, so keep the base, subtract the indices. 3 minus 1.5 is just 1.5. So we'll write that as 2 to the power of 3 on 2. Let's look at the 3's. We keep the base, subtract the indices. The indices, we've got 1.5 here, minus 1, which just gives us a half, so 3 to the power of 1/2. Minus 8/3, which again we'll just leave as 8/3 for now. What else can we do? We see that we've got 2 of these have got a fraction of a half, the 3 out the front there. Let's get this into the power of a half as well, so I'm writing the 2 to the 3 on 2 as 2 times 2 to the half, multiplied by 3 to the half, and that's all minus 8/3. So just that move we did there, so 2 to the 1 multiplied by 2 to the half gives us 2 to the 3 on 2, so we did like an index rule in reverse there. I did that so that we've got these two numbers here with the same index. So now I can combine those. This is the square root of 2 times the square root of 3, which is the square root of 6. So we can simplify this a little bit further to give me 2 root 6 minus 8/3. That's the exact answer. If I wanted to get a decimal approximation for this, I could put this into the calculator, write out the first few decimal places, but this is the correct answer, which is exact. So the total arc length going from x equals 0 to x equals 2 along this curve, the square root of x cubed on 3 gives us this answer, 2 root 6 minus 8 on 3.